Welcome, everyone. My name is Brittany Todd. I'm a member of the Fabric Leadership Team. And thank you all so much for joining us today for the 9th installment in our Stitching Together Innovation with Fabric Users, which is led by Dagim Mindaye. Before we begin, I would like to share a few housekeeping items. The webinar will include a live question and answer session following the presentation. Please note the chat feature has been disabled. If at any point you have a question, please type it into the Q&A box at the bottom of your screen, and we'll answer it during the Q&A session. Last, this webinar is being recorded and will be shared with all registrants. Today, we are joined by our presenter, Dagim Mindaye. Dagim is an international undergraduate computer science student at Alfred University from Ethiopia. He focuses on computer networking, distributed systems, and applied machine learning. His current research works on programmable data planes, Kubernetes orchestration, and transport protocols such as QUIC. He has been involved in projects integrating P4-enabled networking with Kubernetes services to study dynamic load balancing and routing. Beyond research, Dagim serves as Vice President of Alfred's African Student Association and collaborates with fellow computer science students on innovative side projects. I will now pass to Dagim to start the presentation.
Hello all, so this is our project P4Q, which is an in-network load balancing for Kubernetes. So before we get into our actual project, let's go to our motivation. So container orchestrators are great at what they do. They're tools for rapid deployment and rescaling of containerized application. But orchestrators like Kubernetes have a limitation. They lack direct integration with the network layer. So our work is bridging that gap by leveraging data plane and Kubernetes control plane programmability. So let's have a high level look over Kubernetes. So Kubernetes is a leading orchestrator tool that organizes containerized applications in different pods. Let's take a distributed web server, for example. Here we have our Kubernetes cluster, our n number of nodes. You can have however many running the pods, and a control plane that oversees them. How do clients connect to this deployment? We have our client coming in here to the switch. The data goes into the switch, and then comes the problem that we're trying to solve through our project, which is which pod should be getting this traffic. So this is our project, and basically what we're doing is we have a protocol-independent switch architecture in our P4Cube data plane and a P4Cube plugin that oversees our worker nodes. It collects every type of information about them, including the pod or node health, and then it sends that information to the P4Cube data plane for it to actually do the load balancing. And what this gives us is it decouples the control and data path. There is no middleware required, so we won't be struck by any type of bottlenecks. We have line rate dynamic load balancing. So what is that plugin actually doing? It informs the programmable router about the state of the pods. We have the container deployments and the node pod service running, and these extract the worker node's IP address. And then they also extract the node port, TCP port. They create the control packet, and then they send it to the control packet to the switch. But more than that, they also wait for the cluster's changes events to occur, and if they detect any type of change, they do the whole thing again. And the changes can be, like as mentioned below, it can be pod or node failure, CPU or memory overload, or even new pod deployments. And once they detect this, they do the whole thing again, and then they send the control packet to the switch. This is the packet that we will be sending to the switch. It includes the deployment's virtual IP address, node port service port number, the number of replicas, and the different IP address replicas, the replicas of the IP addresses. And this will be encapsulated in a UDP header. and also it uses a custom destination port so that once we send this to the switch, it knows if this is coming from our servers and not coming from a client. So this distinguishes it as a control packet and not as any other packet coming from a client. So for example, in our project we used 7777. So whenever it sees 7777, it knows it's a control packet. And then we have our data plane. This is where most of our project logic will be happening. So we have packets coming in from the left to our parser, and then it has the Ethernet header going all the way down, IPv4 header, and then the TCP header, and then here it checks the destination ports. For example, here you see the UDP destination port. If it's 7777, it knows that it's a control packet and it starts treating it accordingly, and it knows it's not any other ordinary packet that's coming in. If it's 4433, it will know that it's QUIC, and we'll see how this is important because in our project we treat TCP and QUIC differently. We'll see that in a second. And then it will do checksum, and then in the ingress pipeline, we already know what packet type we have. If it's a control packet, it treats it accordingly to do the load balancing. It takes that information and then it uses it to update the cluster info. If the packet type is TCP or UDP, it checks the SYN value. If it's 1, it knows it's an initial handshake. So it does ECMP hashing, which distributes the load equally amongst the nodes that we have. And then if the SYN is 0, then it just decodes the server ID and then rewrites the header, and then it goes to the LPM table, computes checksum, and the parser just reassembles our packet and then sends it to the correct node. So let's look at how we treat TCP and QUIC differently in our project. So in TCP, if the pool of the available server changes at any point, hash-based load balancing will break the TCP session affinity. So how we solve this is TCP does not have any specific field to identify the flow. So what we did is we encoded the server ID into the TCP timestamp value. So whenever a packet that's already initiated a handshake comes in, we just decode the server ID from that TCP timestamp value, and then we send it to that node. But it's different with QUIC. QUICs can bypass the load balancer after the handshake because it has a destination IP address and it has a connection ID which specifically identifies to which node it should be going. While this is good because QUIC will allow like your IP address and UDP port to change, it also has some security implications like spoofing or targeting a certain nodes to overload them. So that's something we're working on. And to evaluate our project, we used Fabric and we implemented it using Go and P4. So we have 10 nodes set up with 1 Kubernetes control plane, P4Q router, and 1 client connecting to it. And this is what our slice looks like, which we will set up in a second. And the software and tool used for these are Kubernetes, Nginx web server, Apache, HTTP benchmarking, and AIO QUIC. But so why did we choose Fabric? It's possible to build really large networks. Each virtual machine has enough CPU, RAM, and space to run virtual P4 switch, Kubernetes cluster, apps like Nginx server. And with the help of Fablib and Jupyter Hub, it's easy to build and rebuild a slice and install all the necessary softwares. It's especially useful for team projects too. And there's the Fabric community support to help you with whatever problem you may run into. So to set up our slice on Fabric, what you need is a Fabric account, a sliver or bastion key, and a project. So you'll open Jupyter Hub, download into Jupyter Hub the slice installation guide, which you'll find in our GitHub. And then we'll update the top cell with your project ID first, and then you just execute the cells one by one, and then we'll follow the instructions. Next, we'll have the demo. In our demo, we'll download the notebook. I'll show you how you set up the slice, and then we'll do some testing with Nginx servers, and we'll change the number of replicas too. Then we'll install and test quick deployment, and we'll have some Apache benchmarking examples. So to download the notebook, you go into our GitHub, P4Cube setup, and then you'll go to the raw file. You'll copy that raw file URL and then go to the terminal in your Jupyter Hub. And here you'll type wget and then paste that URL. And then once you refresh, you will see the P4Cube setup. Here we'll need to do two things. One is change the project ID and the site. To do this, we'll go to the Fabric portal, go to experiments, and then choose the project you're working on. Go down, and here you'll see project ID. So you'll copy that, and then come here and you'll paste the project ID. And to choose the site, you'll go back to your Fabric portal. And here you'll see all the available sites. For our project, it doesn't really matter because we don't use lots of resources. So for now, we'll just use RUTG. So here we'll come and type RUTG. And that's basically your setup ready to run. So let's go through them one by one. So on the first one, you're just connecting to your Fabric Slice API. This will help you interact with Fabric. The second slice, this is where you will be reserving your slice. If it's your first time doing it, it will just reserve it. But if you're running it again after reserving your slice, it will just give you the SSH commands to log in into each of the nodes. So you'll see it here. This is where we change the MAC address of all the nodes to match with the controller program, configuring the IP address on the switch to enable connectivity between the hops. And this is where you'll install the P4 software on the P4 switch node. You're cloning a bunch of stuff here, and then here you'll generate the command to run the switch emulator, which we'll do right now. So we'll copy this, and then we'll copy this SSH command and log into our P4 switch. So after we log in, we will copy the command that was generated. So we'll copy that. And then go to our switch and paste it. And then you'll start that our switch will start listening to incoming traffic. Here is where we'll initialize our routing table for the P4Q router. You will see that all rules have been installed now. Installing the Docker, Kubernetes on master, and all the nodes. This is where we'll set up our cluster. And here it's very important because this cell will give you a token that you will need to copy and paste into the next cell. This token is specific to your Kubernetes cluster. And here you'll join all the worker nodes to that cluster. This is configuring networks for the Kubernetes. This is where you'll be cloning P4Q repo onto the master node. Let's log in into the master node. So we'll copy this, go over to our terminal, and then paste the SSH command. And now that we're logged in, we'll check the amount of nodes we have. Here you see that we have all 10 nodes and our control plane all running and ready. Then we'll check our pods. Here you'll see we have 10 pods currently deployed in our 10 nodes. We can also check from the P4 switch how many deployments you have running right now. And to do that, we just run simple switch CLI and then register a read replica count. And here you can see that we have one deployment currently running with 10 pods. Oh, maybe I had, okay. Give it a second to video. Okay, here we're just setting up each of the nodes and installing all of the required tools on it. And then we'll check if we actually have load balancing on them. So what we need to do that is run a curl command directed to that switch, and then we'll see that it will send the traffic to different nodes every time we do it. So we log in into the client with a SSH key that has been with a SSH command that has been generated. So here we run the curl, and you see we get different nodes every time we ping it. Here we'll downscale the first deployment to 7 nodes. So we'll go to our P4 switch and do the same thing again. Here you'll see we don't have 7 nodes and 10 nodes anymore. We have 7 of them now. And now we're going to do another deployment that has 3 nodes instead now. So if we go to the master now and do get pods again, here you'll see one that says nginx2. That means that we have another deployment now that runs on 10.0.0.3. So when we run that, you see it again here. And in the P4 switch, if you run register read again, you'll see a second deployment that has 3 replicas. This is where you'll install QUIC as a third deployment. So you run all of these commands. This here will install QUIC dependencies on the client. It says it's already satisfied because I've already done it. You can also clone the AIO QUIC here. And here you can see 4433. This is what will tell our switch that this is a QUIC packet, so it will treat it accordingly. And here you can see that a push has been received for get. So you can go over to your client and run this, and you will see that this works from the client side too. So first we'll go to the AIO QUIC examples directory and then paste that. And then here you'll see that a response has been received for get. And now we'll do some experiments to test our QUIC. So this is another Jupyter notebook. You can install it from our GitHub again, the same way we installed our setup. The first cell is just connecting to the Fabric API again. And the second cell will install stress-ng on all the nodes, and we'll download our experiment scripts. There you'll install A/B benchmarking, and then remove all the deployments except the first one to keep it simple for our experiment. And here, when you'll set the stress to true, give the script name, and we'll have 10,000 requests being sent, and 500 will be concurrent. give it a URL, and the type, choose if you want it to be load aware or not load aware. If you do LA, it will be load aware. If you don't, it will not be load aware, and it will do the non-load aware balancing. So this is starting the load pattern on the worker nodes and starting the client. So it will take a couple of seconds. So you see it, it's going. It will be. We'll continue on to the next cell once it says that the experiment is over, and then we will get our results. So this cell is where we'll be getting our results. And here you'll see all the results, like we've sent 10,000 requests, 500 were concurrent, and all of the requests were completed. Here you'll see the how long each of these took. And compared to other solutions to just like setting up another middleware or having extra hops, this is a faster approach, as there's no need for an extra hop or a need of another middleware. So our project does solve that. And here we're just cleaning up all the stresses and stopping the stress on each node. So we'll give it a couple of seconds and it should be done now. Yep. And now it will say CPU overload has stopped. So now it's done and all of it has been cleared. So this was our experiment. And now I'll pass back to Brittany.
Thank you so much. I really appreciate it. What a great presentation. Now we're going to move over to our Q&A. We'll begin with some questions that were submitted during the presentation. So our first question, oh, I see my video is not on. Apologies for that. Our first question is, in the current design of P4 Kube, could an attacker potentially inject a fraudulent control packet?
In principle, injection is possible if an attacker gets access somehow, but that's not the focus of our research right now. There is no cryptographic authentication, but it is possible if you find a way for the switch to distinguish between the client and the control packet and be sure that it is coming from the server side and not from the client.
Thank you. Our next question, what are the limitations of evaluating P4 Kube in a fabric testbed?
So our limitation is you don't get real life or production scale numbers. The only thing we have in Fabric is you can compare one implementation against the other, and that's what we did.
Thank you. Our next question, how fast are the resources for the P4 Kube slice reserved? How much time does it take to fully set up the framework?
Resources are typically available within a bounded reservation window, but framework setup is consistent and reproducible across experiments. So it might take you as long as a couple of minutes, maybe like half an hour, but it is reproducible.
Excellent, thank you. Our next question, what is programmable in P4 Kube?
So it is programmable at two levels. One is the data plane. Here we have our P4 defining the parsing or like breaking up the packets that are coming up, and then we'll mash them and we'll do the forwarding logic. So we'll send it to the node. It's programmable in that level. And then second is at the control plane level, where Kubernetes will dynamically update our P4 tables.
Thank you so much. Our next question is, what are the future directions for this project?
Our main direction for this project right now is working with QUIC and the spoofing and load balancing bypass concerns we have.
Thank you so much. And this is our last question. What do I need to run your experiment?
You would only need to have a Fabric account, a Sliver or Bastion key, and a project that's already set up. So you just need to go to the GitHub, clone it, and then upload it to your Jupyter Hub, and it's easy as that.
Wow, thank you. Well, thank you again to our presenter, Dagim. In addition to our presenter, we would like to acknowledge the behind-the-scenes team that will be listed on the slide, who work diligently to bring this webinar to production. And of course, thank you to our audience for your participation in today's webinar. In addition to a recording of this webinar, we will also email everyone who has registered a list of resources. This slide deck will be shared along with our Connect with Us form. We hope that you will reach out to the Fabric team for questions or support. Our webinar next month is Mastering Fabric Tips and Tricks webinar on October 21st at 3 p.m. Eastern Time. This webinar will be focused towards existing users, AI researchers, and testbed administrators. We would appreciate it if you could forward the information to the relevant users in your community. As a final reminder, please submit your Fabric matrix and make sure your project description in the portal is up to date, as we will use that information for outreach, including our website. Thank you again, and have a wonderful day, everyone.